In December 2024, China switched on a machine that could reshape how humanity generates electricity. It's called a supercritical carbon dioxide turbine, the first one anywhere connected to an actual power grid. Engineers have chased this exact goal for over 6 decades. Most experts assumed it wouldn't materialize for another 10 years. But China made it happen, installed it inside a working steel plant, and started converting waste heat that everyone else simply discarded into usable electricity. The figures are hard to accept at first. Using identical heat input, this machine produces 50% more electricity than the old system it replaced. It's also half the physical size. And rather than relying on water like virtually every power plant on the planet, it operates using carbon dioxide, the same gas your lungs release with every exhale. This isn't some minor upgrade. We're talking about potentially replacing the steam turbine, a technology that sat at the heart of electricity generation for over 140 years. If you find this useful, hit that like button and subscribe so you don't miss what comes next. Before examining what China actually built, we need to understand why the traditional method of generating power carries a massive flaw most people never consider. Think about where your household electricity originates. It might come from coal, natural gas, nuclear reactors, or massive solar installations. But regardless of the fuel source, the final step remains almost universally identical. The plant heats water until it converts into steam. That steam rushes through an enormous wheel lined with blades. The wheel spins. That motion turns a generator. The generator produces the electricity flowing out of your wall socket. That's essentially how nearly all power generation has functioned for over a century, an idea tracing back to the 1800s. Sure, engineering refinements have improved things somewhat. Today's turbines use stronger alloys and burn hotter fires. The interior of a modern steam turbine reaches temperatures capable of melting most metal objects you'd encounter daily. But the underlying concept hasn't shifted. Heat water, generate steam, spin a wheel. It's essentially identical thinking from the Industrial Revolution, just wrapped in more sophisticated hardware. Here's the part that might genuinely surprise you. Even today's finest steam turbines only convert about 35% of their heat energy into usable electricity. For every 100 units of heat burned, merely 35 become productive power. The remaining 65 simply dissipate into the atmosphere or nearby rivers as wasted warmth. More than half of all energy we consume vanishes before it ever reaches your home. That's an enormous problem at global scale. Essentially, every power plant on Earth burns fuel while letting most of that energy slip away. Something we've simply accepted because that's how things have traditionally been done. But scientists have recognized this problem for a remarkably long time, spending decades searching for something superior to steam. The world burns billions of tons of coal alongside vast quantities of natural gas annually, largely just to boil water. If you could push that 35% efficiency figure toward 45 or even 50%, the resulting impact would prove massive. Less fuel burned, less energy wasted, substantial savings alongside reduced pollution simultaneously. The math is straightforward, but making it reality proved extraordinarily difficult. Engineers eventually realized the solution wasn't building an incrementally better steam turbine. They needed an entirely different working fluid instead of water, and the fluid they settled on was carbon dioxide. Understanding why requires knowing about a peculiar state of matter almost nobody discusses. Everything surrounding you exists in 3 basic forms: solid, liquid, and gas. Ice represents solid water. Liquid water is what you drink. Steam is water existing as gas. But there's actually a 4th form most people never encounter, one appearing only when you push temperature and pressure extremely high simultaneously. Push any substance beyond a certain threshold, and something peculiar happens. The liquid and gas states stop remaining separate entities. They merge into one unified form. Scientists call this a supercritical fluid. Picture it this way. A liquid resembles a heavy, powerful individual. A gas resembles a light, swift runner. They're fundamentally different, performing entirely different roles. But in the supercritical state, it's as though they've become one person simultaneously heavy and fast. Strange to contemplate, yet completely real. Something scientists have understood since the early 1800s. Now, here's why carbon dioxide proves so remarkably special. Pushing water into this supercritical state requires temperatures of 374 degrees Celsius, alongside pressure around 220 atmospheres. Serious extreme conditions harsh enough to damage most metals while costing fortunes to manage. Carbon dioxide, meanwhile, reaches its supercritical threshold at merely 31 degrees Celsius and roughly 70 atmospheres. 31 degrees resembles a warm summer afternoon. The pressure requirement proves considerably easier to manage too. Compared against supercritical water, supercritical carbon dioxide seems almost surprisingly straightforward to produce. Once carbon dioxide crosses into this state, something remarkable occurs. It becomes nearly as dense as liquid water, yet flows through pipes and machinery as effortlessly as a gas. This combination makes it essentially ideal for electricity generation. Here's why density matters so profoundly. Inside any turbine, pushing more material through the blades every second directly translates into more generated power. Steam remains light and diffuse, requiring an enormous machine to push sufficient volume through for meaningful output. That's precisely why turbine rooms inside major power plants rival airplane hangars in scale, some machines large enough that a person could walk inside the casing. Supercritical carbon dioxide, however, carries enough density that you can push a substantial quantity through a dramatically smaller machine. The blades shrink considerably. The piping shrinks too. The entire power system becomes remarkably more compact. And due to how the underlying physics function, considerably less energy gets wasted throughout the process. These systems could theoretically reach 45 to 50% efficiency, a substantial leap beyond steam's 35% ceiling. But recognizing something should theoretically work and actually building it represent two entirely different challenges. If supercritical carbon dioxide proves this superior, why did constructing one take until 2024? Building this particular machine proves incredibly difficult in ways easily overlooked from outside. The first obstacle involves heat combined with chemistry. Achieving optimal results requires heating the carbon dioxide to roughly 700 degrees Celsius before it enters the turbine. At that temperature, most metals gradually stretch and deform under sustained pressure over time, a phenomenon scientists call creep. Inside a rapidly spinning turbine, even minor dimensional changes can trigger mechanical failure. Carbon dioxide compounds this problem further, pushing carbon atoms directly into certain metals' internal structure under high heat and pressure. Over time, this weakens the metal, making it increasingly brittle. A brittle blade spinning at tens of thousands of rotations per minute under tremendous pressure represents real danger. So engineers require specialized alloys engineered at microscopic levels, specifically to resist both thermal stress and chemical degradation. These exist and perform reasonably well, but cost significantly more than conventional steel. And since nobody's run these machines for 20 or 30 years under real conditions, nobody's entirely certain how they'll perform across a full operational lifespan. That uncertainty makes investors understandably cautious. The second major obstacle involves the heat recycling system, arguably the hardest component of all. One primary reason these systems achieve such efficiency involves capturing heat from their own exhaust and feeding it back into incoming fluid. Making this work requires moving enormous heat quantities through remarkably thin walls, while both sides endure roughly 200 atmospheres of pressure simultaneously. The device accomplishing this resembles nothing else in power engineering. Engineers etch microscopic channels, some thinner than a human hair, into flat metal plates, then fuse thousands together into one solid block, containing millions of tiny internal pathways. The result proves remarkably compact and excellent at transferring heat, but nearly impossible to inspect once assembled, impossible to repair, and extremely expensive to manufacture. Should even a microscopic crack develop internally under 200 atmospheres, consequences turn serious immediately. The third obstacle involves rotational speed. Because carbon dioxide proves so dense, the turbine itself can remain small, but smaller turbines must spin considerably faster to generate equivalent power, often reaching tens of thousands of rotations per minute. At those speeds, conventional oil bearings would overheat from friction and fail within hours. So engineers invented entirely new bearing designs, some using magnetic fields to suspend the spinning shaft with no physical contact, others experimenting with bearings floating atop a thin layer of the carbon dioxide gas itself. Both functioned successfully in laboratories, yet remained complex, costly, and unproven across decades of demanding industrial operation. All these challenges combined explain why, after over 60 years of research and enormous investment across numerous countries, nobody successfully connected a supercritical carbon dioxide system to an actual power grid until December 2024. That's precisely when China changed everything. The China National Nuclear Corporation announced they'd activated 2 supercritical carbon dioxide turbines at a steel facility in Jiangsu province. Each unit generates 15 megawatts. Together, they comprise a system called Chuantu-1, the first functioning grid-connected supercritical carbon dioxide power unit anywhere on Earth. Chuantu-1 burns no fuel of its own. Its purpose involves capturing waste heat. The steel plant was already venting skyward and converting it directly into electricity. Steel manufacturing generates enormous leftover heat that historically just got released unused. Chuantu-1 captures that heat before it escapes and puts it toward productive use instead. The results prove quite impressive. Compared against the previous steam turbine, Chuantu-1 generates 50% more electricity from identical heat, occupies 50% less space, and heat recovery efficiency jumped over 85% across a full year. The steel plant now generates over 70 million kilowatt-hours from heat previously wasted entirely, translating into roughly $4.3 million in additional annual revenue. A factory now earns millions annually from heat that formerly just vanished into the atmosphere, without changing its steel-making process whatsoever. The only difference involves a smarter machine sitting within the energy recovery loop. Complete technical specifications haven't been publicly released yet, so certain headline figures deserve some caution until additional data emerges. But the core achievement is confirmed regardless. This system operates continuously on a commercial grid connected to an actual working factory. Running a machine inside a laboratory represents one challenge. Running it continuously inside a factory, performing reliably day after day without shutting down for repairs, represents an entirely different test. Chuantu-1 passed that test. That shifts the entire conversation. The question no longer concerns whether these turbines can function properly. It concerns how quickly the rest of the world catches up, and what happens once these systems appear in applications considerably more critical than a waste heat loop. Let's be honest about what this announcement means, since certain headlines proved more dramatic than reality warrants. The technology works. That's significant news. For decades, these turbines existed purely within research papers and small laboratory setups that never left the building. Transitioning toward commercial installation isn't a minor step. It's an entirely different challenge requiring functioning supply chains, safety certifications, and authentic operating conditions no laboratory could replicate. Successfully making that transition means the metals held up, the heat recycler functioned properly, the bearings survived, and the control systems handled pressure without catastrophic failure. But where engineers chose to deploy Chuantu-1 reveals plenty about where this technology really stands. It's not attached to a nuclear reactor, nor serving as the primary turbine inside a major coal or gas facility. It's capturing waste heat at a steel factory specifically, a comparatively safe testing environment. Should the system encounter problems, the only consequence involves the factory generating slightly less bonus electricity. No city loses power. If these turbines were ready for everything, you'd expect deployment inside new nuclear facilities where efficiency gains would matter most. Starting with waste heat recovery demonstrates the industry proceeding cautiously, building confidence incrementally, while gathering the long-term data major decisions require. That caution represents the correct approach. Before anyone trusts this inside a nuclear facility, they need evidence of reliable operation across 10 to 20 years. Bearings need considerably more operational hours logged. Heat exchangers need to demonstrate they'll survive decades without cracking. None of that data currently exists, since no system has operated long enough to generate it. What Jiangsu 1 represents is the beginning of that collection process, the opening entry within a track record that must expand before this technology reaches the applications that matter most. Once that track record builds, the possibilities become quite remarkable. Small nuclear reactors half their current size. Factories converting waste heat directly into revenue. Power systems compact enough to fit inside a ship. Solar installations functioning effectively, even in arid regions where water remains too scarce for steam cooling. Other nations pursue this identical objective too. The United States, Germany, South Korea, and Japan all maintain active research programs. But China transitioned from research toward actual deployment first, and in technology development, that head start tends to compound over time. Every hour Jiangsu 1 operates generates data no laboratory ever could, feeding directly into improved designs and greater confidence for subsequent projects. There's something amusing buried within all this too. People discuss moving beyond the steam age into some new era, yet both technologies are essentially identical in age. The steam cycle was documented back in 1859. The cycle supercritical carbon dioxide utilizes was documented in 1872. After roughly 150 years of parallel development, we're finally advancing by merely 13 years of underlying physics history. But sometimes 13 years changes absolutely everything. The steam engine didn't transform the world the day someone invented it. It transformed the world once it became reliable, affordable, and sufficiently well understood to trust universally. These emerging turbines now stand at the beginning of that identical journey. The first commercial unit is operational, and data keeps accumulating. Should engineers resolve remaining challenges around materials, heat exchangers, and bearings at meaningful scale, the machine that quietly activated inside a Chinese steel plant could eventually become as commonplace as the aging steam technology it aims to replace entirely. That transformation might require another decade, or perhaps 20 years. But for the very first time in this technology's long history, that countdown feels genuinely real and tangible, rather than purely theoretical. If you enjoyed this video, hit the like button and subscribe so you don't miss what comes next. Turn on notifications so you're first to know when we cover the next major shift in energy technology. So here's my question for you. If supercritical carbon dioxide turbines become the new global standard, which industry benefits most from this shift? Nuclear, steel, shipping, or something else entirely? Let me know your thoughts in the comments below.